So with our conducting sphere, I will represent it as a tin, nickel, aluminum, magnesium, silver. No, that's not dark enough. Sorry. I guess we have to deal with nickel. There we go. It's a conducting nickel sphere. Now what's going to happen is this. Let's positively charge PVC pipe. So here's our PVC pipe. I'm going to draw it like this. Look at that. Such artistic ability, Mr. Abdullah. Look at that. Wow, that looks just like the PVC pipe. There we go. Now we're going to have it all positive like this. Okay. Now, here is what happens with a conducting sphere. This thing is electrically neutral, but because the charges are free to move, the negatives immediately separate themselves from the atoms that they are bound to and literally just aggregate over here, leaving like positive charges all on the edge here. Okay, and so what's going to happen, and I'll put it on a little platform here, is I'll write it like this. The positive PVC pipe causes the, okay, I'm going to use some chemistry knowledge here, electrons, I don't want to write that out, in the conductor to rush over because they're attracted. Okay. To the PVC pipe. There we go. So that's what happens with the conductor. Now, with the insulating balloon, there's just a slight and subtle shift that works like this. Essentially, what we have is a balloon. I'm going to give it a nice bubblegum color. So here we go. That's bubblegum color? That's some pretty gross looking bubblegum. All right, so the situation with an insulator, I'll just kind of draw it here. If you have an atom of insulating or a molecule of insulating material, typically it's electrically neutral. So you have like a little blob of positive and a little blob of negative, and they're kind of on top of each other like this, if you will, all nice and neutral. And essentially what happens is the following. I'll just kind of show it here. When you have a positive charge, what happens is that the negative moves a little bit closer, so you have a slight separation of charges. So what's happening in the balloon is, whoa, that was weird. Made that weird noise. What happens in the balloon, I'm just going to recopy this here, PVC pipe. There we go. Wow. The wonders of 10-year-old technology. Okay, so what's going to happen is you have this positive pipe here, and there's just this slight charge separation throughout the balloon. So what happens is on the edge here, you have the negative charges just slightly separating from their respective positive charge. They can't move freely because insulators don't let charge move. So you get this induced dipole. I'm not going to make you use that word. And then what happens is the little positive charge lining here causes the next row to kind of do the same thing. Let me see if I can kind of copy that. There we go. There we go. So that's what I'm trying to do. Kind of get a few rows of these charges, just to kind of show you all what it does. Yeah. So we get this little row here. Close enough. And then we get kind of I'll shrink this. See if it does that. Fit it all in there. Oh, isn't that cute? There, just like that. So we get this little slight separation of charges kind of induced throughout the balloon. So what happens with the insulator is definitely different. So the positive pipe causes a slight shift in charge such that the negative charges move slightly toward the pipe, and this causes an attraction. Totally related physics, but definitely a different effect. Now, part 3, I'm just going to finish up this page because I think it's a great thing here. So we've got two charges, each of +2 microcoulombs, and they're separated by a distance of 2 meters. How long must their masses be, or how big must their masses be if the gravitational attraction is to balance their electrical repulsion? I have a suspicion we're going to get a really big number because electrical force is just so much bigger than gravitational force that we're going to need some big masses to balance. So don't forget mu. I know you like how that always pops up in class. Mu is 10 to the -6. This is the you are not getting the physics teacher you want. You're getting the physics teacher that is capable of showing up on 5 hours of sleep. Mu, 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 mu. Okay. Sorry, that was a little weird. Let's go ahead and actually set up this problem. So we have electrical force balancing gravitational force. Again, balance means equal. So we have K, Q1, Q2 over R squared. And Fg, they have equal masses, so we'll say G, mass times the same mass over R squared. Now here's something amusing. I can cancel the R squareds on each side. The other thing, I'm going to do one more little bit of math. This works out to m squared. So I have K, and these Q's are the same. So this is Q squared. So Q1 equals Q2. Same Z's. So we have KQ squared equals G m squared. I'm going to divide both sides by G. And so I can actually get m equal to the square root of K over G times Q. Let's go ahead and do that now. So the mass will be 9 times 10 to the 9th divided by 6 times 6 times 10 to the -11th, 6.07 times 10 to the -11th. All under square. Oh, that just looks awful. So m is 9 times 10 to the 9th divided by 6.7 times 10 to the -11th. Sorry. All under square root. And we'll times that by 2 times 10 to the -6th, and let's see what mass we get. So, with this in mind, I will actually multiply this out, and we'll see what we get. So, 9 times 10 to the 9th divided by 6.7 times 10. Sorry, 9 times 10 to the 9th divided by 6.7 times 10 to the negative 11th. That under a square root times 2 times 10 to the negative 6th gives me, wow, 23,180 kilograms. That is not an error or a typo. I will double check my math, but I do not think that is an error or a typo. This is really kind of the disproportion between gravitational strength and electrical strength. So that's questions 3 and 4.